Yesterday, or the last time we looked at this lesson, we went through and worked on some equations and determined special situations. Okay, we determined whether there were all values for solutions, which means there are an infinite amount of options, or no values, which means no number would ever work to solve an equation. Okay, if we take a look here, I kind of grayed out the no values. So before we move on, I want to look at the situation with all values for just a minute. So I want to kind of take a second and see what actually was happening when we determined that all values were true. Okay, so remember that means that any number you choose for the variable is going to make the equation true. So for a problem like number 1, like I showed you here, if n was 3, 3 equals 3. If n was 12, 12 equals 12, and so on. If we look at number 2, if I take a look from this point right here, if I picked a number for t, okay, so let's say we chose the number 1. So if I chose the number 1, I wanted t to equal 1. Oops. So if I said t will equal 1, if I were to replace the t with a 1, we would be able to see what's going to happen. So let's actually do some erasing here. And let's see what would happen. And don't erase yours, just watch. If t equaled 1, instead of 2 times t, it's 2 times 1 plus 6. And I'm even going to go back up to my original. Equals 2 times 1 plus 3. So all I'm doing is taking the number 1 and I'm replacing each t with the number 1. And I'm going to do the math. So on the left, I get 2 plus 6, which equals 8. On the right, if I follow the order of operations, I get 2 times 4, which equals 8. So if t is 1, this works out. Okay, now that should work for any t that I would possibly pick. Okay, what if I wanted t to be 100? Well, instead of a t, I'm going to write 100. Again, I'm going to the very beginning and replacing the t with 100. So on the left, I get 200 plus 6. And on the right, I get 2 times 103, which is 206. They equal each other. So again, just to show you what that means when we say all values or all solutions. Oops. There we go. Sorry about that. All right. So just a little bit of review for that. So now going back to where we left off, our job is going to be, we're going to do number 2. Write the other side of this equation so that the equation is true for all values of u. Okay, so write the other side of the equation so the equation is true for all values of u. So we need to create a situation. Let me zoom in a little bit here, sorry. So that the left side and the right side become a situation where we have all values. Okay, so again, let's go back to this other slide and let's see what happened when we got all values. We ended up with a number equaling itself. On number 2, if I go back to what my options were here, I think your notes ended up looking something like this. we have a number equaling itself. We have a number equaling itself. 18y equals 18y. Variable equals itself. So if you end up with the left side and the right side being exactly the same, it's all values. I'm going to back up even a little bit more. Take a look right here. Is the left side and the right side actually exactly the same? It is. 2t plus 6 equals 2t plus 6. Let's back this up. Right here. Negative 4 plus 3x equals negative 4 plus 3x. Exactly the same on both sides. Once you simplified, you didn't even really have to solve, right? And then if we look at this one, 18y equals 18y. So something common happened here. Once we simplified, or at any point in the solving process, the left side and the right side were exact mirror images. So we can use that information to help us on number 2. So the left side is exactly the same as the right side. Okay. Now, you could take the shortest route possible to answer number 2 here, and knowing that if the left side has to be exactly the same as the right side, technically you could answer the question like this. Write the other side of the equation so it's true for all values. I could do what you see here because it's literally the left side equaling the right side. And you would be correct. The only thing is we do want to try to push ourselves and challenge yourself a little bit. And although this is very clever and it works and you would be correct, let's think about some other options that we also have, other ways that you could go about this question. Okay, one thing to think about is on the examples that we just looked at, we really noticed that the left side, I'm sorry, here we go. The left side equals the right side once we simplified. Okay, so if you see like right here, once we simplified, the left side equaled the right. Once we simplified, the left side equaled the right. So what we could do here is we could start simplifying. So I could distribute and get 6u minus 12 plus 2. Combine like terms here and get 6u minus 10. So I know that the left side is going to simplify down to 6u minus 10. So I could make 6u minus 10 be the option of what the left side could equal, or I'm sorry, what the right side could equal it for this to be true for all values. Okay. Another option is I could take the 6u minus 10 and I could rewrite it a little bit differently. So, for example, instead of 6u minus 10, I could write like this. So I could kind of rewrite and undo the distributive property. And I could rewrite the 6u minus 10 to look like I did over here, 2 times the quantity 3u minus 5. So I'm basically just, with the hanger problems where you had to, write an equation that matched the hangers, there were a lot of different ways that you could represent what was happening. Same kind of thing here. 6u minus 10 is the same as if I were to distribute a 2 to 3u minus 5. You have options. As long as the left side ends up equaling the right side exactly, you will have all values be solutions. Get as creative as you want or be as efficient as you want. Either's fine. So now let's look at number 3. Write the other side so the equation is true for no values. So let's take a look, and I blacked out the all values, and I'm looking only at the no values, and let's see what happened. So if I look at the very end of each of these, I don't have a variable left, and my left side and right side do not equal each other. My variable's gone, and my left side and my right side are numbers that will never equal. Same thing down here. My left and my right, the variable is gone, and they're never going to be equal. I didn't really go all the way to the end here, but v plus 4 will never equal v. If I back up to where we simplified, okay, so let's look and see what happened when we simplified. So in the first one, when I simplified, I had 3n on each side, but I was adding 3 to one side and adding 1 to the other side. It's like the left side got a little bit of a head start from the right. They'll never catch up. Okay, you can think about this as saying, well, if you have three n's, and I'm going to add 3 to it. But on the right side, I'm only going to add 1 to those 3 n's. Well, the right side's never going to catch up to the left side because the left side started out with 3 extra, and the right side only started with 1 extra. Okay. If we look at the second problem right here, I have 20d plus 4. So on the left side here, I have 20d, and I add, well, on the right, I just have 20. Nothing gets added to those 20d. So the left side is always going to be 4 more than the right. They cannot possibly be equal ever. There's no number ever on the planet that when I add 4 to it is going to be the same as it. So we can back up to the simplified version here and help us see even the original question down in that second row. If I take my x, I'm going to erase this so you can see. If I take an x and I add a half to it, it's never going to be the same as an x with a third added to it. It can never be equal. No matter what x I pick, if I add a half to it and then I add a third to it, I'm not adding the same amount. And the same thing on, let me erase this really quick. The same thing on the last one here. If I have v and I'm adding 2 to the v, it's never going to be the same as if I subtract 2 from a v. No matter what number my v is, adding 2 is never going to be the same as subtracting 2. Okay, so what you end up having is like the same number of variables on both sides, but different constants. So the constants are the numbers that don't have a variable. So, for example, don't write this down, but if I had, 2d plus 7 equals 2d plus 3. This is the same number of variables. I have 2d's on the left and 2d's on the right. Different constants that's these. Right? Because if I have the same number of the variables on each side, they're going to cancel out when I solve. Okay, so I just wanted you to understand the words I used. You can definitely adjust the words to as you see fit. So for example, if we think about how we handled number 2, I need to make sure that this side has 6 u's, right? So if I were to simplify, I got 6u minus 12 plus 2, right? When we simplify, and then I get 6u minus 10. So I need to make sure it has 6 u's, but doesn't have minus 10. So it needs to have the same number of u's, so it has to have 6 u's, but cannot have a negative 10. Right? I need a different number of constants. I need a different just plain number. Okay. So, let me rewrite this. 6u plus 10. 6u minus 7. 6u plus 11. 6u plus 8 million. As long as it has the 6u, right, but does not have plus 10. Because remember, we want this to be a situation where the left and the right are never going to be equal to each other no matter what. And we're going to keep practicing. Okay, the next page. Part 1, complete each equation so that it is true for all values. So you'll hear this called many solutions. Okay, is another option. Infinite solutions is another way you might hear that. So remember, in this case, we need the left to equal the right. Exactly. So the left has to equal the right exactly, like perfectly, right? So let's look at number 1. The left side is 3x plus 6. So that means I need my right side to equal 3x plus 6. Now the thing is we're given a piece. Okay, let me zoom in here for you. So we're given a piece. Let me fix this. That's going to bother me here. I'm given the 3 that's going to be distributed. Well, when I distribute the 3 times x, I'll get 3x. What would have to be in this spot so that when I distribute the 3, it becomes a 6? That's all we're thinking about here. So for a second, think about what would have to be in this empty spot so that when I distribute the 3, I get 6. Hopefully you said 2. All right, let's take a look at the next one. Remember, the left side has to equal the right side. So x minus 2 is going to have to equal x minus 2. Now, this is where it gets a little interesting. Okay, so I have a negative sign in front of my parentheses. So let's remember what that means. That means that there's really a -1, right? So I really have a -1, and this -1 is going to get distributed inside. Now, -1 times -x is going to give me positive x, right? What am I going to have to multiply -1 by? Okay, it's going to go right here. What multiplied by -1 is going to get me a -2? What times -1 is going to get me a -2? Hopefully you said 2. Let me clean this up a little bit. So again, -1 times -x is x. -1 times +2 is -2. Let's check out our last one. Now, this one looks a little interesting. Nothing we can't handle. Let's simplify this side. Okay. What's happening here is everything is being divided by 5. So 15 is being divided by 5. And -10 is being divided by 5. Okay. So you could think about this as 15x divided by 5 minus 10 divided by 5. Okay. It's just the way it's written as a fraction. You can assume everything's divided by 5. So 15x divided by 5 is 3x minus 10 divided by 5 is 2. Now, if you need to back up a little bit, if you need to rewrite this as 15x over 5 minus 10 over 5, do that. I want to make sure that you can see where everything came from. So this is going to equal something minus 2, right? Well, it's got to be, my left side has to equal my right side. It's got to be 3x. It's as easy as that. 3x minus 2. Oops. Okay, so for the next part, we are going to complete each equation so that it is true for no values of x. Okay, so that means that we have no solutions that will possibly work. Okay, so true for no values and no solution, same type of thing. Okay, now we do have the same equations that we had above, except there is one typo. I need you to, in this third section here, I need you to make that plus 2. Let me make that clear. Plus 2. That's a typo. I don't know how that happened, but it's okay. All right, so we need no solution. So if we go back and review what happened with many solutions, so with many solutions, we needed the left and the right side to be exactly the same. We needed the same amount of x's, and we needed the same amount with our constants or our numbers. Same number of x's, same constant, right? Everything had to be the same on each side of the equation. Now, with no solutions, if we look back at our notes, I'm going to highlight again where the simplified parts are. If we look, our variables are the same, but our constants are different. And it isn't just that we have n's on both sides, we have 3 n's on both sides. And if we have 3 n's on both sides, they're going to cancel each other out. And these constants that were left, because the constants are different, we're going to get a no solution. Okay, if we look here again on the second one that I'm highlighting, same number of variables. So I have 20d on the left and 20d on the right. Constants are different. I have 4 on the left and none on the right. These are different, right? Down here, my variables are the same. I have 1x on each side, but my constants are different. I have a half on the left and a third on the right. If we go to our last one, my variables are the same. I have 1v on the left and 1v on the right, but my constants are different. I have positive 2 on one side and negative 2. So we have the same number of variables on both sides, but different amount of constants. Okay, so the part that needs to be the same is just like the many solutions. With these special cases, it's a special case. Variables on both match each other. That's a clue that it's a special situation. When you have 3 x's on both sides, that's a clue it's a special situation. If the constants are the same, it's going to be all solutions or many solutions. If the constants are different, it's going to be no solution. Okay, so let's go ahead and figure out what to do here on in number 2. So my left side is 3x plus 6. So because I need my variables to be the same, I'm going to need 3x on the right because these have to be same. But my constants have to be different. So whatever number I ended up with here, it can't be 6. So this is not what we want though. Okay, this is not where we're looking right now. Okay. That's kind of like the end game. We want to figure out what's going to go in this space. So I need a number that's going to go in this spot so that when I distribute the 3, it is not 6. Because remember, I distribute the 3. 3 times x gets me 3x. 3 times whatever is here needs to get me not 6. So what number can you put in that box so that when you multiply it by 3, you don't get 6? This can be any number that's not 2. 5, 10, 11, -7, 243. Any number that will not make 6 when you distribute. Right? So whatever number you put there just cannot become 6 when you distribute the 3. You're going to end up getting 15. It's not 6, so we're going to be good, right? Okay, let's take a look at the next one. So I have x minus 2 on the left. And if we look at the right, when you see the negative sign in front of the parenthesis, there's really a 1 there. So we're going to distribute this -1. So I'm going to get -1 times something. And then I get negative 1 times negative x is plus x, right? So I'm going to have my matching x's, which is good, right? But I need to make sure that these are not the same. My constants. So I cannot end up with a negative 2 on the right-hand side. So what number can I place in this box right here so that when I multiply by negative 1, I don't get negative 2? I cannot have negative 2 end up in this box. So what number can we put here that will make it so that I don't get negative 2? Pick any number. Any number that when you multiply negative 1 does not get you negative 2. 10, 12, negative 7. Anything. I'll put 4 in that spot. Because negative 1 times 4 is negative 4. It makes them not the same. Now, it can get a little confusing as to what's the actual answer that we're trying to put here. And let me clear out some of the junk. The actual answer is what you put in this box. So if I want this number to become negative 4, then I need to have a 4 in this box. These are a little trickier because we are looking at the end. We're looking at the end to help us figure out the beginning, if that makes sense. Let's look at the last one. So if I simplify the left side, if we think about it like above, it's 15x over 5 minus 10 over 5. So we get 3x minus 2 equals something plus 2. So we need to figure out what's going to go in this box to make sure that we have no solution. Okay, remember, same variable amounts, different constants. So if I look at my constants, they are different. That's good. I need my variables to be the same. So that means I would need to have a 3x in this box. So if I go back up to my problem, I need a 3x. Have to have the same variable amounts, different constants. And that's it. So on your own for number 3, at the very bottom, describe how you know whether an equation will be true for all values or no values. So take everything we've talked about, things you've written, and come up with your own kind of way to describe how are you going to tell the difference between true for all or true for none. And that's it.